Today I would like to talk about Variational AutoEncoder VAE. So before we talk about VAE, we talk about a normal autoencoder. So what is autoencoder? Autoencoder is that what is auto is the same, so the input and output is the same. So encoder, which we have the input going into a network multiple layers, and then there's a middle layer which we call bottleneck, and then it passes through the decoder, and then you'll be outputting the original image or number or anything. So this is the autoencoder. Now variational autoencoder, the difference between autoencoder and variational autoencoder is the bottleneck. And the bottleneck for autoencoder is a number, is a vector. For VAE it will be a distribution. So this is the difference. Now the goal of the variational autoencoder is to find a distribution QZX of some latent variable Z. So probably we look at this graphical model. So we have observation, for example, the image. We want to learn some representation of the image Z, the hidden variables. So in this direction, we will be using something that is found to generate a new X using this distribution, which is this part. So this part we also call it as a generator. And for this part, it is a recognition part, which is to recognize what should be Z before we generate the X, the new X. So we have some training X. We try to see what is a hidden variable. So given X, we want to find a Z. And then we learn this Z, and after that, we can use this model to generate new X. So the variational autoencoder, the training process will be to train this network. After that, we take this part of the network to generate new samples and using the distribution that has been learned. Now, some example of a variational autoencoder would be like, for this man, we passing through this autoencoder, and then we extract the distribution. So this is the sample. This is the example of an autoencoder, which we have like small single value 0.6, skin tone a single value of 0.8. So this is a vector, and then we pass through the decoder, and we get back the same people. Now for the variational autoencoder, the difference is that rather than a single point, we have a distribution. So we can select a particular point inside this distribution to generate a new image. So we can sample multiple images that might not be inside the original image training set. So this is the idea. Now until here, I have covered the essence of the variational autoencoder. You can see that the autoencoder we call the recognition model to recognize the things, to learn the hidden states, and the generative model to generate a new model. So this is encoder and decoder. Now here we have understand the objective of a variational autoencoder. Now from now on, I will be explaining the maths behind the variational autoencoder. If you are not interested in the maths, you can skip it if you want to. Now let's talk about the maths. So how the loss function is being defined in variational autoencoder. Now let's understand about what is the loss function. In the loss function, we'll be using something called a KL divergence. So what is KL divergence? A KL divergence will be for P and Q. P is a distribution and Q is a distribution. Will be almost this will be almost the correct one, which is we making use of this entropy, the Q entropy, and minus away the P entropy. So we get their entropy difference, which is the KL divergence. But in KL divergence, we have something that is like with respect to. So Q and P and Q will be doing it with respect to P. So now the thing is that we'll be using the PX as the something that has happened, and in the situation in the P and Q. So according to that, we need to replace this PX. We need to replace this QX into PX. Now we have this formula. Now the KL divergence is always bigger or equal to 0. And the reverse will not be the same. So now, for example, if you have a normal distribution and you have an exponential distribution, they will be very, very different. But if you have a normal distribution P and then with a normal distribution with the same mean and variance, they will be almost the same. Now this is an example. Now for example, if you have only 2 points and 2 events, and the event for happening, let's say this is A, this is B, happening A is 0.5, happening B is 0.5, the same for Q. If you sub this into this formula, you will get the KL divergence as 0 because they are exactly the same distribution. Now if let's say the chance of happening A is 0.2, B is 0.8, the Q is both 0.5 as before, then you will not be 0. And KL divergence, now first of all, we already talked about KL divergence. Now we talk about the graphical model. So for a graphical model, as I explained before, given an observation X, we want to infer what is the hidden state Z that is used to produce X. Now by making use of this formula, given X, we want to find Z. According to base formula, it will be base equation will become this, and we can make the numerator become the X and Z joint probability. Now the problem here is that computing the PX is very complicated. Why? Because let's say if you want to calculate PX, you want to make use of PX after you CZ and PZ. So we want to calculate all possibility of Z. So we want to integrate over Z. And let's assume that Z is something in a very, very high dimensional. Then we need to integrate many times. If we are in a Z dimensional, we want to integrate Z times. And this is very complicated. So a more clever idea is being proposed, which is to use approximation for PZX. So this approximation will be using something from a tractable distribution QZ, and normally a normal distribution, which it is easier to calculate. Now the problem becomes we want these two distributions as close as possible. So we want to infer QZ, and this is this is the probability we want to get. And now this is the KL divergence of it. And according to the formula we have, this is when we sub the formula in, and this is the equation. And we do some of the handling. So we just reorganize, become this. And the log AB will become log A minus log B. And we distribute QZ into this log A and log B. So become this formula. And the log PX. So this summation of QZ over Z will become 1. So log PX, we can extract it out to the left side, and then we can put the KL to the right side. So, and then we do a negation of all the sign, will become this formula. And you can see that for log PX, it will be a KL divergence plus variational lower bound. So we call this variational lower bound. Why? Because given X, log PX will be a constant. Now what we want to do is to get this value as small as possible, which in turn we want to Alright, there's a mistake here. So I just changed the direction of z and x. So you can see that this is this KL term here, and then we've moved the log px, which is this term, to the left side, and then we just keep this on the right side. And this is the term we want to minimize, and you can see that since given the x, log px is constant, so to minimize this KL is equivalent to maximize this term, and we call this term as a variational lower bound. So now let's see more on this variational lower bound, which is equivalent to this term, which is the log px minus this term, and this is equal to this variational lower bound. So we do a splitting of the numerator here, and we do a since log a times b equal to log a plus log b, so we just split it into this form, and then we distribute this qz into log a and log b. Now, so on the left hand side, this is the expectation of pxz with respect to qz, which is which can be written in this form: z with respect to qz. Now for this form, this is the KL divergence of so given this variational lower bound, we have this come up with this formula after some derivation, and then this can be seen as the left part and right part. So the left part will be the expectation part, and the right part will be the KL part. So the KL part will be like QZ is similar to PZ, and the left part will be the reconstruction error. So why this is a reconstruction error, we can see here. So why this is a reconstruction error? And remember that we mentioned we want to make use of a normal distribution because it is easy to have a closed form. So we assume this pxz is a normal distribution. So it's a normal of the this is the mean and this is the variance, covariance. And with this normal distribution function, it will become something like this. And if you add a log, because we have a log here, we can see that this is proportional to this formula, and this is x minus min z and x minus min z here. So this is, we can consider this as a square reconstruction error. Now for this another part, which is the KL, QZ and PZ. So these two parts. So this the right part will be a regularization part to make sure that the reconstruction has some variance that is similar. Now we can look at the case here. If we have this reconstruction, the left part being assigned with a less value, then the distribution will be deviated from the prior. And if the regularization part, which is the KL part, is less, it will try to cheat by stringing it to a point. So we are having this regularization so that it can become a normal distribution. It can become a proper distribution with some variance there. So you can view this as a regularization KL part. And let's look at the loss function of the VAE, variational autoencoder. So since we want to maximize the variational lower bound, so we want to minimize the negative of this variational lower bound. So minimize negative of L is equivalent to maximize L. So we have a loss equal to minus L, and we have this the representation here as we derived before. Now why it is good to assume that the PSZ here is a normal distribution, the PDF. So Oh, I correct title here, so I just correct it as we assume this PZ and QZ, which we make it as a Q5Z X here, so they are equal now. So just a syntax. So as normal. So now the KLQZ parallel QZXZ. So I change it to this Q5Z ZX Z condition on X parallel with a PZ. So we assume this PZ as a normal from 0 to 1, and we have this QZ as the normal with a variance of this, and with the mean of this and variance of this, and by that we have a closed form formula as such, which we can prove it. And subsequently, TR is the multiplication of the diagonal value. It's a summation of the diagonal value. So you can become a summation of K on the diagonal value. And for this part, it is the transpose of this term times this term, so it becomes a square. This is a transpose here, so the K become this one. And for this term, since it is the this is the determinant of the variance, and it can becomes the product of the diagonal value of this covariance. And after that, we can move the pi, the product out as a summation according to a log formula, and we can move all the summation out here. Now for the numerical stability, we substitute exponential variance with the normal variance, and becomes the result here. So we now subs this into the K out term here, and become this formula. So this is the closed form formula for the loss function. And now we are going to talk about how to do the reparameterization trick. First of all, why we need a reparameterization trick? Because there is a problem if you want to do the backward propagation for the VAE. Now, since we have these two set of parameters, we want to minimize it. So how we do is that we get the sigma. We do the partial derivative for it, get a sigma plum, and when to do the differential partial differentiation, we make this phi constant. So we have this theta plum, and after getting it, we plug into the next formula. Now we do it differentiate according to phi, and we fix the theta plum we got from the previous formula, and we do this iteratively. Now, so to calculate the first one, there is no problem. The problem is calculating the second one. So for the first one, d over d data. So this is the loss function is this formula. Now we can make this d over d data go inside the expectation to become this. So the expectation become this one according to this Monte Carlo estimation, and this term, since they are by phi, they will be 0, and this will be the final outcome if we do a partial differentiation according to d data. Now by d phi, there is a problem because we have a z sample from z following x. So since we have a phi here, we can put the d phi inside. This is where the reparameterization trick comes in. So the trick is to rewrite the exponential e to put the phi inside the function. Now we have this, this is the original form. Now this is the new form where we have a p, this epsilon, and we change the z into this formula. So what is this formula? So this is the variance, this is the mean, this is the epsilon, which we sample from 0 and 1 normally, and it times the sigma, which is the variance. So remember, we want this q phi zx becomes this normal equation. So we make z sample from this is equivalent to making z sample from this. So we can make z as a, so according to this mean and variance at this, we can make this formula, so with a random variable. And now with this trick, this is the previous one, and after this trick, z now is, so with the reparameterization trick, this is the O loss function, and this is the new one with reparameterization. So the z now becomes z for superscript L, which is equivalent to this equation which we introduced before, and a random variable epsilon. Now we have this zl, which is from this random variable, and now rather than using z, we use a zl, so the back part is the same. Now we can put the dd phi inside the expectation, because there is nothing, there is using phi here. The phi is only inside this zl, so we can put inside here. So this part become this because of a Monte Carlo estimate of the expectation, and we distribute the dd phi inside the equation. So we take this down and we take this down again, but this is inside the differentiation. Previously, z is a random sampling from the distribution of q z given x. Now it is it has a deterministic form, and which is depends on this normal random variable. So it takes this random node out here, the blue node, from z to something outside, so that we can do the backpropagation successfully. So this is a trick that is being done here. Alright, I hope that you understand on a high level how VAE works. So hope you enjoy the practical part, like 3 minutes in front and the 70 minutes of the theoretical part after that. And first of all, but I want to say that this is a note that I have done for myself. So if you are not do not understand anything, please feel free to leave it on the comment so that I can help to answering that. Thank you.